We need. Anybody's.
It's a great pleasure to have Professor Vijay Ganesh from Georgia Tech for today's seminar. And for all of us mathematicians, Vijay is a world leader in creating SMT solvers for very hard math problems. So we can hopefully all just get our open problems to him and he can create a better tool for us. So it's a great pleasure to have you.
Thank you. Thank you again for inviting me to this seminar, and thank you all for coming to this talk. So today I'm going to talk about some new tools we have built in the broad context of AI for math. And I will also take this opportunity to give you a little bit of a context about what this field is. It's a very fast-moving and emerging field. And also the roots of the field, all the way going back to SAT solvers and SMT solvers. So just to add to what Ayush mentioned, I did my PhD in formal methods, primarily aimed at software verification. In that process, I built solvers, SMT solvers, and SAT solvers, and provers. But I also do a lot of work in logic and proof complexity. But this talk will be focused on tool building. Okay, and specifically, how joint embeddings can play a role in the context of auto formalization. So just very quickly, I've been building SAT solvers and SMT solvers for a very long time. If you are not familiar with the term SAT solver, it's just a tool that takes as input Boolean formulas in conjunctive normal form and decides whether they have solutions. The term SMT is a short for satisfiability modulo theories. These are tools that are aimed at solving first-order formulas, first-order theories like Peano arithmetic, Pressburg arithmetic, and so on. Even if they're not decidable, we still build the tools for them. And the value of doing so is that they enable us to build a very good software engineering tools for debugging, for automated testing, for formal methods, for program analysis, and so on. And I've applied this in many different settings like AI for math, AI for science, etc. And one particular line of research that I focused on early on in my career was the use of machine learning to make solvers more efficient. So allow me to give you a one line or a few line summary of that line of research. So when we use the word solver and we build these tools, these solver tools, what is it that we are really doing? What is that code representing? Abstractly, that code is just a proof system. So what is a proof system? A proof system is just a collection of proof rules, inference rules that you can use to construct proofs. And Lean is a proof system. A SAT solver is a proof system, but focused only on propositional logic. So the ultimate goal is to automate mathematics. Notwithstanding Gödel's and Turing's results, we still, that is our ultimate goal. Now, why does machine learning play a role here? Like, what's the connection? You see, when I build a proof, my goal is always to build the shortest proof. As a tool, I want to build, given a formula, I want to build the shortest proof. And the task of building a shortest proof is an optimization problem. And this optimization problem can be solved using machine learning. Partly because solvers produce a lot of data. You can use that data to train these models. So in other words, your solver algorithm may have many choice points in it, and these choice points can be implemented using machine learning techniques. So the next part of the story is when LLMs came online, for me, it was very natural to see the connect between LLMs and ML systems and proof systems like Lean. And I kind of quickly jumped onto that bandwagon. So here is my team. They do most of the work. I do most of the talking. These are the students who build the tools. So Pritish is the one who built this particular tool. And the rest of the team is working on various AI for math projects. By the way, please do feel free to interrupt me at any point and ask questions. That makes it much more fun. Thank you. All right, so why do we care about AI for math today? A variety of reasons. We have proof systems, implementations of proof systems such as Lean or Isabelle out there, using which you can formalize mathematics and thus be sure that your proof is correct. There's a lot of value to formalizing mathematics in these theorem provers. But there is a problem. And the problem is that the effort required to formalize theorems can be very high. It's not that straightforward to formalize theorems. So people have been trying to sort of put layers on top of these proof systems, these tools like Lean, to make it easy for others to be able to use these systems. Unfortunately, until the arrival of LLMs, most of these attempts were not very successful, let me put it that way. But since the arrival of LLMs, it has opened up a vast array of possibilities. Why so? Well, LLMs allow us to build tools or functions that take as input natural language and produces output formal language, right? So it can do this translation from NL to FL, albeit still not perfectly, but there's a lot of work to be done, but we have a good start right there. Furthermore, we can use these kind of ML systems, as I mentioned a minute ago, to do proof synthesis. Proof synthesis is the problem of, given a conjecture, your goal is to generate a proof. A naive way to think about that is you search through the space of all possible proofs, but that is not efficient. So you have to come up with all kind of heuristics to figure out, given statement, what is the tactic or proof rule that I apply in order to get the next statement and so on until I prove my theorem. And this, as I mentioned earlier, can be solved using machine learning. So that's another reason why we are bringing these tools together. And finally, ML can be used for discovery of conjectures. So you could have a lot of data out there. You could feed it to a ML system and you could do symbolic regression on it, try to fit an expression to it, or even sort of ask these systems about, can you give me a new conjecture, for example? So for all these reasons, it makes perfect sense to combine machine learning and automated reasoning and interactive theorem proving. So people, of course, have built in the last 2 years, there's been massive activity in this space. There have been, many tools that have been built, like Alpha Proof, Alpha Geometry are some of the more famous ones that can do problem solving. DeepSeek Prover is another one, and so on and so forth, right? But my focus is to build an ecosystem for AI for math, which is open source, which can be used by anybody. And I know that I'm competing against hundreds, maybe thousands of engineers at companies like DeepMind and other places who are, experts at building these transformer models, and they can win by scaling and creating very good data sets. So in other words, people who are working in AI for math in academia have started off with a big disadvantage, unless you somehow join them, which is also on my agenda, by the way. Is if I can't beat them, then I join them. So the point I'm trying to make is that you are competing against scale. So as you well know, LLMs are getting this amazing performance thanks to scale, which is not exactly, from an engineering point of view, it's probably not the smartest, but it's working. So, why not use it? So that's what they're doing. And they also have the resources to create amazing data sets that allow them to produce almost magical results. So by contrast, so then what are the options left for us? And in some sense, the rest of my talk will focus on techniques. So my focus is on techniques, not as much as scaling or data sets, although those are very important too, and we must somehow get that as well. So how can we build creative techniques that address some of these issues? So within this context, our goal is to build this AI for math ecosystem, and it will have many parts to it. One part would be an intermediate language, which we call WERN, which takes us, which allows you to build like a front end, just like in a compiler. You have a front end wherein you feed your natural language and it translates to an intermediate language, and then the rest of the tool chain takes as input this intermediate language and translate to Lean and so on. There's a lot of value to doing that, which I can talk offline. And at the back end, you have this auto formalization tools and proof synthesis tools. You can think of auto formalization if you're a person who has a compiler background as a compiler. It's taking a very high level language and lowering it down to a relatively low level language. Okay. So the problem that I'm going to focus on for today's talk is primarily auto formalization, although every auto formalization tool also has an element of proof synthesis built into it. The reason is that almost all mathematical proofs out there are incomplete. So you do have to somehow reconstruct the proof at the back end. Okay. And of course, it goes without saying, there's a lot of verification and checking that has to be done, because it could be that the input itself has errors in it, but also that the tool might introduce errors as well. So to be more precise, the problem statement here is we are given as input a pair of theorem and proof in natural language, and we want to produce the equivalent formal language theorem and proof. In this particular tool, we want to produce lean. That's the goal. And when we say equivalent, I want to be a little bit more precise about it. So there are two properties we really care about. The first property is type correctness. In other words, the output theorem and proof pair must be type correct according to Lean's compiler. Lean's compiler must say this type checks. However, that is not sufficient to say that the output produced by the auto-formalizing LLM is equivalent to the input, right? So we have to somehow also prove that the output produced by the LLM is indeed the same sentence as the input theorem. And the proof is also has the same core semantic content to it. Unfortunately, this problem is impossible to solve because your input is natural language and your output is a formal language. There is no way we are going to be able to cross-check the two. So we have to then fall back on all kind of heuristic techniques. And there is always, we'll have to do some human verification. There's no way of avoiding that in this setting. So that just keep in mind. Okay. And
There's one way
yeah,
that people have talked about. I mean,
Okay.
this problem of getting the statements right.
Yeah.
Is a massive issue, right?
Yes,
Lean will check the type for you and say, yes, the proof is right. The proof of what?
exactly.
So one, this is what Christian Zegedy
Okay.
talked about when he was here.
Okay.
Some years ago, is that I argued with him about exactly this. You know,
Yeah.
it's great that you're going to auto-formalize things, but how will we know that you're formalizing what
Right.
you say we are?
Right.
What you say you are. And he said, well, you know, you have a theorem. That theorem is important because it's used somewhere else.
Right.
So when you go to use it in the grand structure of mathematics,
Mhm.
we'll be able to error check semantic correctness in the long term.
Right.
It's very similar to what actually happens in the practice of mathematics.
That's fair.
But maybe you don't want to wait for the long term. Maybe you want to know right now. So
Yeah,
you actually
yeah.
formalize what
Well,
you say.
I mean, it's a both and. So you do want to have heuristic checks in place locally while you're doing the translation. But as you correctly pointed out, once I'm done the translation and then you say, oh, this theorem is being used at other place, but the proof doesn't go through anymore. Okay, something went wrong somewhere. So yeah, I totally agree. Yeah, that's a good point. By the way, I'm working with Christian as well on, there are various interesting projects I can mention to you about offline. So as I mentioned earlier, there's a lot of activity in this space. So there's a fair amount of work out there already. So there is the Kimina auto formalizer, for example, MMA, Herald Translator. The trouble with a lot of these auto formalizing tools at the moment is that all of them focus on formalizing theorems and not proofs, which is a big problem because there's a lot of, if you were to give them proof to auto formalize, so imagine now you have a tool that's doing a great job auto formalizing your theorem statements. But then you say, you know what, I also want you to auto formalize the proof. And these tools will immediately fail because they've never seen a proof and they will produce a sorry, for example, right? And so they will not work for auto-formalizing proofs. So in other words, there is no escaping the problem of auto-formalizing proofs as well. Yeah.
Recently using Kimina, it will actually generate a mathematical proof.
Yeah.
And then formalize it, feed it into Lean.
Right.
And then tell you whether or not it's been proven.
Right. But I would argue that this kind of proof synthesis, as I mentioned earlier, is a critical sub-problem within the auto formalization space. And it's great that they can do that. Having said that, though, they won't be able to synthesize all proofs, in my opinion. So there's a lot of,
These were very simple.
yeah. So a lot of proofs we don't know how to synthesize at the moment, automatically, right? So we just, we have to some, like, especially inductive proofs can be hard, or certain kind of combinatorial proofs. So I think, yeah, that's great. It's a great start, but we still need this technology. There is some work in proof auto formalization. It's a little bit less explored. Do you have a question or no? A very famous paper early on from Albert Zhang and co. was on this draft sketch proof system that converts NL proofs into formal sketches and then formal sketches into final proofs. This idea of formal sketches is very powerful, actually, because it allows me, it's a form of intermediate language that allows me to have a very rich language in which I can express proofs that are relatively close to natural language, but then has enough precision to it that downstream tools can do the correct job of doing auto formalization. The problem with draft sketch proof is that it's not aimed at lean. So we have to like somehow retool the whole thing or come up with our own tool chain. There's also Form L4, but we couldn't get it to work. I don't think we even had access to the code of Form L4. So why is auto formalization difficult? As I mentioned earlier, there is no clear notion of semantic equivalence between the natural language proof and the formal language proof. The second problem one has to deal with is that LLMs hallucinate, and therefore they'll produce something which has nothing to do with what you gave as input. They'll introduce errors in the process. So they have to have a process of checking for those errors. The third problem that we deal with is there is a scarcity of data. We don't have good Rosetta Stones of pairs of natural language theorem proof and formal language, equivalent formal language theorem proofs. We don't yet have that. And there is a difficulty of like bootstrapping. You have to somehow bootstrap a tool. So you have to hand create a data set that can do the job and so on. Right. So, and as I mentioned earlier, there is a separation of auto formalization of theorem versus proofs that creates a fundamental disconnect between, so the existing tools have these problems. So even Alpha Proof, for example, a very famous tool from DeepMind, you have to do the NL to FL translation, and then you can do automated proof synthesis downstream. There are a few other points. Let me first talk about the last point. As is well known, natural language proofs can be incomplete, or most certainly incomplete, most of them, and sometimes may even have bugs in them, right? Errors, soundness issues. And it's also true that, and this point here, which talks about random few short demos for semantics, what I'm trying to say there is that people have noticed that LLMs perform better if you give them more context, more examples. But how do you do that? How do you give proper context for a given theorem proof pair? In point of fact, the rest of the talk focuses on this problem. How do I create the appropriate context such that a lot of these other problems go away? In particular, LLM will hallucinate less. The correctness of the resultant output will be higher and so on. So this is the core problem that we focus on. So we want to, more precisely, we want to have both high type correctness, ideally perfect, and high semantic correctness. Yeah.
Paper provide a natural language to formal language proof.
Sorry, could you repeat?
Doesn't the Herald paper provide a natural language to formal language proof pairs? I think it has around 50,000.
The Herald translator?
Yeah, the Herald paper.
I do mention it. I believe it's only from natural language to formal theorem statements, not proofs.
I think that is 550,000.
Okay.
I think there is a 50,000 separate
Data set?
provider.
Okay.
Yeah, if I remember correctly.
I see. When was this published? I mean,
I
things.
think February 2020.
Okay. So I'll have to take a look at it offline. So I'm not aware of this. To the extent that we know, it's only for theorem translation.
Right.
Yeah, but we can chat offline about it. Yeah. So we present this proof bridge tool. The proof bridge tool is a bridge between NL and FL, NL for natural language, FL for formal language. And the core idea is this concept of joint embedding. To me, this idea of joint embedding is actually a very powerful idea, and I'll clarify it in a moment what this means. So actually, allow me to first give you the conceptual idea first, and then I'll go into the details. So imagine that you want to train a model and you want to input to the model a natural language theorem and statement. If you are a formal methods person focused on software engineering, it would correspondingly be specifying the properties and the behavior of a software program, except at a very, very high language, but precise enough that it makes sense, right? And now you're wanting to, for your tool, to produce the formal language output. Correspondingly, you're wanting your tool to produce the actual software that corresponds to your specification. So the property that I would like for such a model to possess is the following. It should map in its embedding space, it should map the proof in formal language and the proof in natural language to close enough points in the embedding space if they are indeed equivalent. Put differently, if two things are semantically the same thing, one is written in French, the other is written in English, it doesn't matter to me that they are different. They should be close together in my embedding space. By contrast, if two things are semantically inequivalent, then I want them to be far apart. This is the invariant that I want the LLM to possess. And the entire point of our training is to ensure that our LLMs have this invariant. And once we can check that the LLM has this invariant, we then leverage such, I should use the word transformer, but anyway, it should have this invariant, and then we leverage that to then make the downstream task more feasible. So the way, now let me get into the details. So how does the entire pipeline work? So are you guys okay with that invariant, by the way? Does that make sense? So, I mean, so to me, this is, somebody asked me the other day, because I am in the formal methods community. So we always think about proving correctness of systems. So it's like, how do I verify an LLM? So what does that mean? But, okay, but what is the specification? Like how, so if it's a compiler, I know how to write the specification. For sort algorithm, I know how to write the specification. What is the specification for an LLM? We don't know. So that question prompted me to go in this direction. So the answer that I came to was, if two things I as a human know are semantically equivalent, then in the LLM's embedding space, in the mind of the LLM, they must be close by. And if they're inequivalent, they must be far apart. If I can check the LLM against this invariant and verify that it adheres to this invariant according to some notion of verification, then I win. So I have a notion of specifying the property of the LLM irrespective of the task it's being used for, as long as I can pin down this property for that specific task. So in the context of auto formalization, the way I pin it down is by saying that the natural language theorem proof pair and the formal language theorem proof pair must be close by in the embedding space and far apart otherwise. In the context of where I'm using an LLM to translate specifications into code, the specification and the corresponding code must be close by and far apart otherwise. And this is to me a sign of intelligence, the ability to know that two things are equal, even though they're represented in a very different form, but they're semantically the same thing. Yeah.
So is this fundamental, I mean, you gave the analogy already.
Yeah.
right, which is translating English to French.
Right.
French.
Yeah.
Is there anything fundamentally different between that analogy and what you're trying to do?
Everything else is how we implement it.
Right, okay,
Yeah.
but that analogy.
That analogy, yeah. So you have a proof written by a French mathematician. They prefer French, I realize that. And then there is an English mathematician, or American mathematician writing the same proof in English.
But even on a more abstract level.
Yeah.
And you have a French
Right.
phrase and you have an English phrase, and you can talk about how close those two you know, whether one is really a translation
Right.
of the other.
Right.
Or,
Exactly. I mean, this is an abstract idea.
Okay.
And this idea can be used as a way to check the correctness of the LLM. And what I'm trying to say is that the idea that I'm presenting to you right now is a way for me to check the LLM. And I can make it mathematically aligned using this idea. I can make it scientifically aligned, meaning I want to align my LLM with physics. Okay, here are two ways of representing the same system. Do you think they're equivalent? Can you distinguish between things that are equivalent versus that are inequivalent? That's the core idea. So now I can make the LLM scientifically aligned, or I can make it aligned in some other way. So in all these, another potential application of this idea is, imagine you have three different proofs. This is my favorite example I mentioned to you earlier during lunch, is you take Gödel's proof, diagonalization proof back in the 1870s. You take Turing's proof, sorry, not Gödel, Cantor's proof back in the 1870s. That would have been a little challenging for Gödel. And Gödel's proof in 1931, the incompleteness theorem, and Turing's proof of undecidability in 1936. The semantic content is very close. They all use a similar idea, which is the diagonalization idea. Once you get that trick in your head, you go, oh, okay, now I understand what's going on, and now I can play with this idea. So can the LLM detect this fact? So even at the level of concepts, can I bring the ideas that are close together in the embedding space that are which are equivalent, and then ideas that are inequivalent are far apart. That's the core principle.
I think maybe you said it before, the embedding space is something that you defined in order to test it, or it's something that's built into the LLM?
It's built into the LLM. So the embedding space is the output of the encoder. So you can think of a transformer. The typical transformer model will have an encoder and a decoder. Typical LLM. I mean, there are decoder-only LLMs too, but anyway. And the point here is that what we are wanting to say is the encoder is taking some input, say a sequence of tokens, and is mapping it through some complicated process into some vector space. That space is called the embedding space. And then the decoder takes a point in the embedding space and decodes it to a sequence of tokens. So now all I'm trying to say is that if two sequence of tokens have the same semantic content, then in the embedding space, they must be close by. So when the decoder reads the point, it does the right thing.
The metric on the embedding space is Euclidean metric on this vector space.
There are many ways you can define it. Yeah, the distance can be defined in many ways. We use one particular way to do it, but I'm sure there are better ways to do it. Yeah.
But this isn't, oh, sorry.
Go
The LLM to me is, you have your tokens.
Yeah.
You have some encoding. And
Exactly.
you have a way to give a distribution of what the next token would be.
Right.
And then a decoding. You're saying, forget about going to the next token, just what happens in the encoding itself.
Correct.
That's the distance.
Yeah, and that's what I'm debugging. That's what I'm debugging. Yeah, sorry. go ahead.
So on the screen that you shared on Zoom, I think only the first slide is showing. I don't know if you
Oh.
can change that.
Wow, that's strange. Nobody's there?
No, there's a couple of people there.
Okay. Is it better now? Because I,
Yes, it's changed now.
okay. Yeah, it's a bit, all the, I'm not reading all this thing that I wrote at the, okay, if I were to expand it out again, now tell me again how it
Yeah,
it
it
looks.
looks good.
Is it okay? Oh,
That's not cheap.
No, it's.
okay.
Yeah.
It has the same problem, yeah.
Is it mirrored?
No, he's just sharing the screen and.
Maybe share the others.
Yeah,
Uh,
mirrored, yeah. So let me see. Display.
Yeah.
Mirror for ViewSonic. Use as,
It is.
it is mirrored, yeah. Okay. Yeah, I'll just keep it at this. Is that okay? Can everybody in the room see it? Okay. So, so once we have sort of accepted this premise, I think the rest of the talk is easy. It's mostly details, but of course, extremely important, but I think you already got the basic idea. So the overall pipeline of the proof bridge tool, it's a 3-step tool. The first step is we train a joint embedding model. The term joint embedding refers to the fact that we have 2 different modalities of input. One modality is natural language, the other is formal language. So we are giving equivalent pairs of formal language and natural language theorem proof pairs. And we construct this model or train this model via contrastive learning. These are well-defined learning techniques. So we are not like inventing a new machine learning technique or anything of the sort. So off-the-shelf tools. And the point of this is that, as I mentioned earlier, in the embedding space, the equivalent natural language and formal language theorem proof pairs are going to be close by. So the blue dot in the picture is the natural language and the red dot is the formal language, and they are equivalent, and that's why they're close by. And if they're inequivalent, they're far apart. Now, the point of training this model is clear in the next picture. I may have to expand this and then I'm going to unexpand it. Is that okay? Because so that everybody can see here. Okay, so what's happening in this picture here is we have an LLM that is then fine-tuned on natural language to lean translations, conditioned on retrieved proofs. So what do we mean by that? So here is your LLM, which is doing the translation. Okay? It is getting as input a natural language theorem proof pair. So that is the query. I'm asking, hey, can you translate this for me? Additionally, I provide some retrieval augmented generation. I'm using retrieval augmented generation to provide some extra context. What is this context? So I send this input to this joint embedding model, which I have pre-trained to have that invariant that I talked about. So the joint embedding model already has this invariant, that the equivalent NL-FL pairs are close by. And the point of this is that this joint embedding model will then generate a set of, so I'm asking both my LLM and my joint embedding model, can you translate this natural language theorem proof pair into formal language? The joint embedding model may not do as good a job as the LLM, because if it did, then I don't need the LLM. But rather, the point of the joint embedding model is to give me some examples. So I'm using diagonalization in my proof. Can you give me some example similar theorem proof pairs? Because I'm giving similar examples and I'm enriching the context in this way, the idea is that the LLM will do a much better job in translating my query than otherwise. That's the core principle. Yeah.
So the joint embedding model, is that just an encoder?
Correct.
And the LLM here is a decoder model.
Yeah.
Okay, and you mentioned like pre-training. So how much data was like involved with the pre-training part of the joint embedding?
I will talk about the data set offline. I mean, so we had like, I think 40,000 pairs of NLFO pairs of theorems and proofs.
And that was pre-trained on a fresh, not on another pre-trained model like a BERT or
No, the joint embedding was trained by us. Yeah,
from scratch.
from scratch.
Okay.
And for the LLM, if I recall correctly, we used some variation of the Kimina prover. And now the LLM will produce an output, which is in formal language, right? This output can now be verified using lean. So what is lean going to do? So over here, and actually during fine tuning as well, we are going to first do a cross entropy loss between the gold standard theorem proof pair in lean and the generated theorem proof pair in lean, and also do type checking. So we make sure that the theorem proof pair makes sense together. And at inference, we also do both syntactic type check using lean and semantic verification. So the way we do semantic verification, so as I mentioned earlier, the syntactic checking is simply the type check. And the semantic check, unfortunately, we have to rely on some heuristic. And the heuristic we use is we use a foundation model to tell us whether or not the natural language proof pair and the formal language proof pair are indeed equivalent. This is by no means perfect, because the foundation model can make errors. But we rely on this technique. It's like an LLM judge. The term that people use for this is an LLM judge. So we are using an LLM judge to check whether or not the output produced is indeed equivalent to the input.
You ask just one, or you ask 1,000 and the both?
At the moment, just one. So, and this sort of works, but yeah, it needs more work. Yeah, go ahead.
There was an extra loop of using the LLM that I was surprised to hear.
Yeah.
Maybe I didn't understand something. So you built the joint embedding.
Correct.
Right? So you asked your question in a natural language. You've now found, because of the joint embedding, a formal proof that's close
Yeah.
to these proposed.
Right.
And then you said you now use again an LLM to kind of refine it, or maybe I misunderstood that.
Yeah. So we retrieve a bunch of proofs that are like
Yeah.
examples.
Yes.
And these examples and some relevant scores associated with them will be fed to a downstream decoder that would then also take as input the natural language query and use these.
So why, okay, so maybe I'm missing how good I'm giving you more credit for the joint embedding than I would have expected. Or that if you had a very good joint embedding, then you would have already been very close to the proof.
Right.
And therefore, it could have just
Right.
been solved by.
Right, exactly. So the reason we don't do that is because we want a cheap way to populate the context with these retrieved proofs. And then the actual downstream translator can be anything. It could even be a foundation model for all you know. You'll have to decode it and so on and create the context, but it could be a foundation model. So in other words, all we are trying to say here is there is a cheap and dirty technique that allows you to give some demonstrations, and we use those demonstrations to populate the context along with the query, and then say, can you come up with other proofs that are similar? And the downstream tool could be built in a variety of different ways.
So the retrieved proofs are not embedded, right?
Right, so it depends how you set this up, but in our setting, we can have a decoder that converts the retrieved proofs into actual tokens, and then augment the context. Right, yeah.
It's like improved few shot learning.
Exactly. It is a form of few-shot learning, except now the machine is doing it in a way that uses a joint embedding. So you're giving, in the few-shot learning, you give examples. So the question is, how can I make my examples relevant to the task at hand? So that's why we are using the joint embedding. Does that answer it? Yeah. Awesome. So, is it changing the screen or still stuck? Is it this?
It's this one.
And now? Okay.
No.
Oh, okay, I see.
No.
Let me try again.
Yeah.
This one? Yeah. Or maybe the entire desktop? That's what I did share previously.
Try this.
Okay.
Yeah, this one. Yeah, it's fine.
And now what happens? No. Okay. What if I share the screen? I think that might be a better approach. Is it showing the screen?
Yes.
And now I go to this. How about now? Working? Yeah. Okay. So now the key idea is across. So now what we are doing is, yeah, as I said, now it's like details of how we actually train these models, right? So the joint embedding is a tool that or a model that we trained for NLFL cross-modal retrieval. And it learns this shared semantic space of NO and FO theorems. And as I mentioned earlier, we want to align the semantic equivalence. So there are a few ways of doing this. We have two different encoders. One is an NL encoder and an FM encoder that maps these things into the shared semantic space. And we are using this mini LM L6 V2 model, which is a lightweight encoder, very small. It's only 22.7 million parameters. That is good enough to effectively capture the semantic similarity between NL and FL. And the way we model the lean theorems, as you are probably familiar, lean uses these tactic style proofs, which is you have a goal state, you apply a tactic, you get a bunch of goals that need to be discharged, you apply tactics until such time that you have no more open goals, and that is your proof, right? And this is actually a very nice structure. So we actually leverage this structure. And what we do is we first encode every state in the proof using Lean Dojo's by T5 proof state encoder. So Lean Dojo is this famous tool it's used for many things, but auto-completion is one of them. And so it has this encoder. We just use that encoder. And it's only 218 million parameters, so it's very, very small. And then we obtain a single embedding for the entire proof, and finally project the encoding into the joint embedding space. Okay. And the key insight here is that we are relying on the proof DAG structure to perform this encoding. And then the way the training is done is through a contrastive learning technique. And the loss function is given over there. You don't have to parse through that, but essentially what it's doing is the term contrastive learning means that you have both positive and negative samples, and you take them into account in your loss function. So the numerator here would be the cosine similarity between positive NLFL pairs, and the denominator is cosine similarity between the negative ones. Okay.
And this is pretty standard.
Yeah, this is very standard. In point of fact, I think similar learning techniques are used for joint embedding of pictures and captions. So if you have pictures and the appropriate caption for it, then at retrieval time, you just want to just give a caption and get a picture. This is a tool called Clip that does this for you. And that's exactly a very similar idea we are using here. So, and as I mentioned earlier, for the auto formalization itself, again, we are using a relatively small model. It's a Kimina prover RL 1.7b to translate NL-FL theorem proof pairs. So the input to the model is your query, which is an NL theorem proof pair, which we want to be translated into lean. And the top K retrieved FL theorem proof pairs from the joint embedding. And we also get the relevance scores for each of them, which allows the model to weigh the importance of each retrieved example.
The score, you run it through lean before you even send it to a score.
Yeah.
They're all syntactically correct.
Yeah.
Semantic. The score is just for the semantic.
Right, exactly. And then we minimize the autoregressive language modeling loss. And the step 3 is inference. So at inference time, a user would send a query to both the joint embedding and the LLM, and do exactly the similar thing as we did for training, except now we also have a repair loop. The way the repair loop works is that we type check the proof and also semantic check the proof using Gemini. And what the loop is doing is you are just you're repairing the query. So you're just sending back to asking the LLM second query saying, here are the errors that we found in the proof during type check and semantic check, please correct them, and so on. And so this, we do up to 5 loops of 5 calls of repair loop and 5 iterations of repair loop. And if it doesn't get it right, we give up. So, right. So now I'm going to give you a quick overview of the experimental setup and how we evaluated this model. So in order to do this, we had to do quite a bit of work to create a meaningful data set. The problem were manifold. One issue was that there's no good data set for Lean 4. So almost all the data sets that we have are in Lean 3, and Lean 3 and Lean 4 are, not exactly compatible, right? So we had to create this data set. It was a lot of hard work, which is based off of this Numina Math Lean and Numina Math 1.5. And finally, we do this. Also, we have this mini F2F PF preparation data set for validation. Again, we had to do a lot of data cleaning and curation in order to get this data set right.
What kind of math is in the data set?
Okay, yeah, that's a good question. So it is, I must say, not very heavy math. It's mostly high school level math at the moment. But the hope is that once we bootstrap the system using this basic math, over time, we'll be able to create richer data sets. Yes.
So I got lost in thought.
Yeah.
This is what you're saying, but what you've just developed.
Yeah.
Should be able to translate from Lean 3 to Lean 4. Is that what you're saying you're doing, or?
We're not doing that yet, but that's a good point, actually. So we should be able to easily translate from Lean 3 to Lean 4 as well. We just need a data set to retool it.
Right.
But once we retool it, then we should be able to do that.
You have the 2 data sets.
Yeah.
Got the formal.
Yeah, no, I
statements, which
completely agree with that.
Much easier.
Yeah.
there, And now you should have.
Yeah.
Okay.
Yeah, I didn't mention one point is that we also informalize. So the way, I didn't go into the details of the data set creation, but one of the things we did was, given the paucity of data, we would start with Lean 4. We would informalize using a foundation model. Informalization is much simpler than formalization. And so once we get that data, we have to somehow curate it and then use it to do the formalization training and validation. But your point is very well taken. So at this point, we just bootstrap a system, and over time, we can produce rich data sets that go from Lean 3 to Lean 4 as well. Yeah.
So
Yeah.
LLM is the one that's doing informalization of this.
Right. The LLM that we,
Then aren't they already semantically equivalent to the?
Right.
LLM?
that's a good, okay, yeah. So if I may generalize the question a little bit. So your point is, it's probably already the case that for foundation models, that this invariant is true, that the natural language and the corresponding formal language statements are close by in the embedding space. That's your point, correct?
Yeah, at least for the ones that your synthetic data that you've generated.
Right. Completely agree. Our point always is that we want to be able to do this with extremely small models. So the informalization was done using
Right.
some very large models.
Okay, so then
Yeah.
you want to make smaller models more powerful.
That's right. Through different techniques, basically. So I'm not going to belabor this in interest of time, because I think we have only like 7 minutes or so, or how much time do I have? So you can take it from me that we have amazing results. So, okay, so, yeah, so basically we, just to kind of show you at least one slide here. That might be relevant. I didn't show you the slide on the joint embedding models, retrieval abilities, but you can kind of see the variety of tools that we have compared against. So we compare against Kimina. We also compare against some foundation models like Gemini, DeepSeek, etc. And then we also have the ablation studies with Proofbridge. So just with supervised fine tuning, retrieval augmented supervised fine tuning, retrieval augmented supervised fine tuning, and repair. So retrieval augmented is with the joint embedding, supervised fine tuning is with the data set, and then repair is that we perform at inference time. We use Lean and Gemini to perform. And as you can imagine, what pass at 32 means that, you basically ask it 32 different things to produce, not just one, and it has a very high accuracy on the validation side. Okay. So allow me to kind of quickly summarize this. So the key technique here is the construction of this joint embedding model that allows us to do this retrieval augmented auto formalization by providing some few short examples and iterative verified guided repair loop that is done at inference time. And we also provide these data sets, Numina, Math, Lean PF, and Mini F2F Test PF. Again, the problems are mostly high school level, but over time, you want to graduate towards research level. And we have performed extensive eval against 10 state-of-the-art LLMs. So the rest of the talk, yeah, I wanted to definitely mention the limitations, which is, as I mentioned earlier, no good automated way to check semantic equivalence. The data sets are still limited. And the next step is, like you mentioned, create richer data sets for between different languages and also research level math. And we definitely want to use all techniques that we can get our hands on, including large foundation models. I want to quickly spend a bit of time on another idea that we invented in our group a while back called reinforcement learning via symbolic feedback. The reason I want to mention this is that this has become standard issue today in the space of LLM AI for math or AI for science. And whenever I mention this idea, they say, oh, by the way, DeepSeek already did this. Yes, except we put it on archive a few weeks before DeepSeek. So I just want to advertise this work for that reason. And the basic idea is quite simple and straightforward. You have an LLM that you are using to do, let's say, auto formalization or proof synthesis, or maybe you want using an LLM for program synthesis or material synthesis. In all these tasks, we have access to domain knowledge and logical reasoning tools, which can then be used to, during fine-tuning and training, to take the output of the LLM, verify it against the symbolic reasoning tool that you have, and provide highly refined feedback to the LLM. And when we published this technique, there was no other such similar technique. All the previous techniques were using such tools, providing Boolean feedback. But here what we are doing is we are providing token level feedback to the LLM, and it dramatically improves the accuracy of the LLM. And the particular setting we used it for was for program synthesis and generation of materials. So now I have some follow-up work with quantum chemists in the context of program synthesis and some materials scientists to come up with new materials. We are building such tools. We're also applying a similar idea in coming up with new theories of physics. That might sound very grand and so on, but it's actually not as grand. So it turns out that we probably know about the standard model, and I'm not an expert in standard models. So if you push me even a little bit, I'll crack. But anyway, let me tell you what the problem is. Turns out that the standard model does not correctly predict the mass of the neutrino. The neutrino mass is predicted by the standard model to be 0, where in point of fact, it does have a small mass. So how do we debug the standard model? That's the question. It turns out the standard model comes with lots of knobs. These are parameters, which means that there might exist a parameter if you just set the parameter, the knobs the right way, it might not only predict the correct value for the neutrino mass, but also for all other particles, the charges and masses for all other particles. Now, if there is no such parameterization, that's an even bigger discovery, because then you say standard model is fundamentally broken. So how do you solve this problem? It's a search problem. And I'm good at search because that's what proof search is. It's a search problem. So I teamed up with a bunch of physicists who are working on this problem, and the same idea is being used there to solve this neutrino mass problem. So we are working in physics as well. So I'll skip over all this, and I want to sort of end with two big project ideas, community-driven project ideas that I'm working on, which are within the AI for math space. One is the logic and complexity lib. So the idea here is that we want to formalize all known logic out there, mathematical logic literature and complexity literature. And to do this, I've teamed up with a bunch of logicians and complexity theorists, and we're collaborating with a variety of institutes. And would be very happy if any and all of you would like to work with us in this effort, because it will require lots of people to be able to do this kind of formalization. Another very exciting project is the sequence lib project. So as many of you know, there is this online encyclopedia of integer sequences out there. It's a very rich data set. And this would go a long way. If you are able to auto-formalize this, it'll go a long way in creating rich data sets from natural language to formal language. And the OEIS has been curated for over 50 years by mathematicians. These are sequences, integer sequences that span a variety of fields. And I'm working with a bunch of people and auto-formalizing this as well. And last but not least, with Ayush, we built this tool called OForge. Well, Ayush built the tool. And the tool is basically a combination of an LLM. Instead of lean, we remove lean and replace it with a computer algebra system. And the goal here is to automatically solve certain asymptotic inequalities, where the lean is, sorry, not lean, but the LLM is really good at doing certain decompositions, and which can then be checked downstream using a computer algebra system like Mathematica. Yeah.
What sort of functions are these? Are they real valued functions?
These are real valued functions, yeah. It would be cool if one could also apply this for complexity analysis of algorithms, for example. That would be interesting, actually. And then another line of work that I've been working on for a long time is combining SAT solvers with computer algebra systems. So here the idea is your SAT solver is like a search engine, which is very good at searching through large combinatorial space of structures, whether they be graphs or proofs or what have you. And then, but the unfortunate thing about SAT solvers is that they don't have deep mathematical knowledge built into them. By contrast, computer algebra systems are storehouses of mathematical knowledge. So by doing this kind of a student-teacher combination, we are able to solve certain combinatorial problems that are otherwise probably not solvable. So we've solved a variety of problems. The problem that I'm most focused on right now is the Ramsey problem. So we're trying to find Ramsey numbers for, like, what's the exact Ramsey number for R38? Well, we know these, but we want also have verification. R45 is the next target. R55 is out of reach, I think. But at least if we can get verification of these numbers using SAT proofs, that would be cool. So with that, I'll end my talk and take questions. Thank you. Yeah.
In your joint embedding space.
Yeah.
When you're looking at, I mean, I don't know if you have the data for this, right? But if you take a formal statement, then there's probably lots of natural language proofs.
Right. Yes.
Typical natural language proofs leave out gaps, things like
Yeah.
this. So I would assume that you then get a point cloud.
Yes. Exactly.
Can you do some kind of, for lack of, if they're in a vector space, the easiest thing is an averaging, but some kind of a summation of this to try to produce a more complete proof. I mean, if I, I'm being cartoonish here,
Yeah.
right? But if this one is here and this one is here, then somehow this proof has an extra little thing in this direction, and this proof
I see.
has an extra thing in this direction.
Yeah, is there like a traversal of that point cloud that you can do to sort of complete the proof in a better way?
Complete proof.
That's a great idea. I don't know yet, like how to implement something like that, but that's something to keep in mind, yeah.
But go on the assumption that most of the proofs we write are incomplete rather than fundamentally wrong.
Correct, that's
then
right.
Just having this embedding space might give you a way
To
to,
complete
even in
it,
there, to complete the proofs and
absolutely. Yeah, it could also be a very interesting way of improving. Another way to think about what you're saying is, it's like augmenting proof synthesis. So you could augment the proof synthesis approach, which right now is a purely search-based approach. But here you could say, well, you don't have to do just a search. Here is a heuristic that gives you a hint in which direction to go. And these kind of embedding spaces could help with proof synthesis as well. Yeah. Thank you very much.
One comment that Neil Sloan is at least progenitor of the OEIS,
Okay.
and he's here.
Oh,
Uh,
he's a professor here. Or?
he,
It's a visitor, permanent visitor.
permanent visitor.
I see.
It's a shame that he, but absolutely.
Only for a while.
Should I contact him and let him know that you're?
Yeah,
So it's amazing actually that he thought of this
Yeah.
back in the day.
40 years ago or something.
More than that, I think that's it's an amazing resource. Yeah.
So, what exactly are you formalizing in the OEIS?
Oh, definitions. So every entry in OEIS is a definition. So it's defining a sequence. And then it's also telling you related theorems, right? So we are just going to create a lean definition. And then we are going to also try to formalize the theorems, maybe try to prove those theorems as well. And that gives us feedback signal in terms of correctness. So the OEIS gives you, sometimes OEIS gives you a piece of code that will essentially print out the sequence for you. But not all sequences are computable. So it doesn't give you code for every sequence. But OEIS gives you the sequence up to some finite bound. So this finite bound allows us to test our output, the lean output we produce. This tool can also be used to go from Python code that is present in the data set to lean. So there are many different use cases for this kind of a tool.
Does your project contain any way of checking if sequences are related to each other?
Right. So actually my student worked on that already. What he did was he built a tool that would create a graph structure of related sequences. And it's amazing, like he did it so super quickly, and he just went through the entire database and built such a tool. It turns out that there is a core set of sequences that are tightly related, but then there is a large number
Very
of sort of
sparse.
individual,
Yeah.
sparse sequences out there.
Is this graph available?
Yeah, no, definitely, I can email it to you.
Yeah.
Yeah, this tool is available, so you can use the tool. Yeah, of course. Yeah. More questions?
Thank you.